All right, so last class what we were dealing with is we were looking into the kind of the understanding some of the differences between proportions and means, and really a lot of the similarities, because there are a heck of a lot more similarities than there are differences between this. But that also means that some of the stuff that you struggled with in proportions, you kind of got to figure out by now. Okay? So today, we're just going to kind of pick up with where we left off. We're going to do a lot of practice today. Today is focusing on the actual mechanics of the thing. All right, so we talked last class. This is just reviewing what we talked about last class. You shouldn't have to write any of this down. Our assumptions and conditions. What were our assumptions and conditions? What did we start with? Independence. Now, independence, generally, we meet with what? Randomization. Okay? And you do want to make sure that you're focusing on the fact that when we're talking about randomization, if we're talking about taking a sample, we have to have random selection for that. If you're doing an experiment, you have to have random assignment. People can't choose for their own because that takes it out. So we've got independence assumption, which is met by the randomization condition, and we had something else, 10%. Because the 10% talks to it being not too big, because there's a certain point in time where when you're drawing without replacement, it changes the probability of the next guy being picked. So we had independence. We had what else? What was new with this one? Normal population assumption. And basically what that states is if your sample comes from a normally distributed population, you should be good. You still don't want the world's tiniest sample, but it's a lot easier to meet this condition. But if we don't know what the population was originally distributed like, which is what normally occurs, we check the nearly normal condition. We check what we have. And the nearly normal condition was saying, okay, in order to kind of get an idea as to what's going on, we need to make sure that we graph. We need to physically see it. We can't just kind of claim, yep, we're good. If you don't actually put it on your paper, it never happened. Okay? So that means you are going to graph a histogram or a normal probability plot, an NPP. We're not going to go crazy with this, okay? You're going to see that today. We're not going to say, ooh, do your bin widths make sense? Is your scale appropriate? What are you doing? You're literally going to zoom stat for a histogram. I like the NPP because they're dots, and I think dots are easier to draw than boxes. That's just my personal point of view. And if you have a small sample size, basically anytime I give you data, draw it. Okay? You want it to be unimodal, at least pretty good metric. The smaller the sample size, the more normal you need it to be. So if it's a real small sample size, you want normal. You don't want outliers. You don't want skew. If your sample size gets a little bit bigger, a slight skew should be okay, but you really don't want like those extreme outliers. Once you get above, like in here we have them between 15 and 40. What I've been seeing a lot of on the test is if they get above 30, we generally say it should be safe by the central limit theorem that the sampling distribution should approximate normal. Okay? Unless we know the data is horrible, terrible, skewed. All right. So we also talked a little bit about some calculations. We said for our t interval, it's not a z interval, it's a t interval here. It's still set up the same way. It's just our notation changes a bit. Confidence intervals are all about the sample. So what is this? How do we say that? Y bar, and what does it stand for? The average of the sample. T star, that's the test statistic for means. N minus 1 is your degrees of freedom. You want to put that number there. Okay? And then times the standard error of your sampling distribution, which is just S, the standard deviation of your sample divided by the square root of n, your sample size. Okay? All right, so go ahead and read through this problem. We're going to kind of take a baby step with this problem. All right? What kind of things do I need to start showing with this? Now with this guy, things are a little bit different than with proportions. Not terribly so, but simply because we do have a difference, I want to go through and I'm going to take this just one sentence at a time. Okay, nothing crazy. One sentence at a time. It just means it might not be the same order that I'll generally do it, but I want you to know how things kind of translate. So if we're looking at this problem, housing market, da-da-da-da-da-da-da, one large community, da-da-da-da-da, sample, da-da-da-da. Am I going to use the number 2008? Am I going to use the number 36? What is 36? 36 is my sample size, correct. So that means I'm going to write that down. And I'm just pulling this stuff out as I go through. 36 bids from potential buyers to estimate the average loss in home value. What am I trying to measure here? Average loss in home value. Is this going to be a proportion or a mean? So that means I'm going to change the notation here just a little bit. Instead of saying P equals, I'm using my mu, because when we're defining this, we're always talking about the proportion. This is what we're trying to estimate. We're trying to estimate the average, what was it? Loss in home value. So far, so good? Just literally going through it one word at a time. The sample showed the average loss was $9,560. What is that number? One more time. Y bar. Good. So I'm going to write that down. Y bar was $9,560. Hello. With a standard deviation of 1,500. So what's that? That is your S. Good. I really like the fact that you guys are giving me the right notation for this. So S was $1,500. I'll just be honest. When I do this on an actual test or an interval, I usually lead with this. Because, really, that's like my reasoning. Because. And I'll put those down after it. I don't care. As long as they're there, you're fine. And you guys have been doing a really good job of listing your pieces. Because even though it comes out and says what everything is, you do need to identify them. All right, the next question says, what assumptions and conditions must be checked before finding a confidence interval? Doesn't mean that we're going to necessarily be able to check them all, but what would we need to check them? So assumptions and conditions. What is my first assumption? Independence. Do we know about the independence in the average loss of home value? No. And to me, I'd be really careful because personally, I think it matters where your homes are because the loss in a home value for a Haymarket house is going to be a lot different than the loss in home value for a house in Houston, Texas. Right. Because you want to be careful. If I'm talking about from one community, then we need to make sure that we're not extrapolating our data to a larger base. So if I'm taking a sample, if my randomly sampled 36 bids came from one community, then I can only extend this to that one community. Okay? So we need independence. Since that guy's a little bit hard to check, what can I use? Randomization. Did we have randomization? Yes. Yeah. Said randomly sampled. Okay. What else do we need for independence? We just went through that. 10%. What number? 36 has to be less than 10% of what? Right, of all bids. So we're going to refer it back to this guy. So we're going to say 36 has to be less than 10% of all bids. Okay. So it takes care of independence. What was my other assumption? Normal population. How do I meet the normal population assumption? So I'm going to actually say that I would need to check either histogram or an NPP. Yes, it's something else to do, but please don't freak out. It's not going to take you a ton of time to do. It is literally a sketch. Just simple, nothing crazy. And when I'm looking at that, what do I want to see? Shape. So what kind of shape do I want? We want unimodal and symmetric. And really with no outliers. And if we've got that, you should be okay. Generally, roughly talking about that. I mean, it doesn't have to be perfect. But you do not want heavily skewed data. And you don't want data with like a crazy redonkulous outlier. Okay. So those are my assumptions and conditions. Now we're going to do the actual 95% confidence interval. So what did I do before I actually did a confidence interval for proportions? Well, first off, we're going to name it. What is the name of this? One sample T interval, and usually T is lowercase. I just am so used to writing a capital letter there. And I'm going to be doing a 95%. Now the formula for this guy is, well, stop with the formula. What would the distribution be here? My sample should follow. Not normal. T. We need to be following a T distribution here. Centered where? Y bar, so that's going to be 9,560 with a standard deviation of what? 1,500 over square root of 36. Now you have a choice. You can either write separately degrees of freedom equals, how do I find the degrees of freedom? N minus 1. Which in this case would be what? 35. So you can either write out separately that your degrees of freedom is equal to 35, or you can just put a 35 right there. It's your choice. I don't care. I just need to see that. Because the T distribution changes depending upon your degrees of freedom. So specifically, we're following the T distribution with 35 degrees of freedom. Now we're going to do the math. The math for this says that it's going to be centered at what you see, plus or minus your T star, depending upon your degrees of freedom, times the standard error of Y bar. So that means I'm going to have, what's Y bar? $9,560 plus or minus. Now, just like we did for a confidence interval for proportions, you actually have to calculate Z star. And I did see a couple of folks who wouldn't do that on their test. So you want to, or didn't do that on their test. I don't think they were rebelling and saying, "Yeah, they will not." How do I do this? How do I get my T star? Inverse T. And we're doing a 95. So 0.5 plus 0.95 over 2. 35 degrees of freedom. Gee, I think I've done this problem before. You're still just going to round it to 2 decimals. What do you get? And that's going to be times that standard error. Now, ladies and gentlemen, if you've got all of this stuff listed out, like I would have just come over here and said, all right, T star with 35 degrees of freedom is equal to 2.03. And I would have said, that is my standard error of Y bar. I wouldn't need to write all that out. Okay, so it's up to you. And just like when we were dealing with proportions, we can use our calculator to calculate this beyond just having to do basic math. So we'll go to Stat, Tests. Am I talking about Z's or T's? T. Am I doing an interval or a test? Interval. So this is the first place I see a T interval, because you see I don't have a one sample T test or T interval here. I just want to make sure you guys see that. There is no one sample. So we're just going to go to the T interval. Now, you have these 2 options. Everybody look at your calculator here. Do you guys see what I'm seeing? We're going to be dealing with data later on today. And that's where we actually put in our observations. And then we can say, well, it's going to be in list 1 and calculate it out. Stats means that they actually gave me these pieces. So go over to stats and enter in the statistics that they gave you. So you went to Stat, Tests, T interval, and then across the top you select Stats. And just like before, calculate. Boop-a-doop-a-doop-a-doop. Doo-wah. There we go. Now this guy is only going to give me decimals if the integers are not that huge. So don't worry too much here. I'm not even going to bother putting down that 0.5. I'm going to say, because in this case we're talking about what? What does my interval represent? What's the context here? Average loss and home value. I'm not going to freak out if I don't put 50 cents when I'm talking about home value loss. So I'm going to say here that my confidence interval goes from, what was that? Making sure I'm putting my units, $9,052 to $10,000. Can't put too many commas in here, it gets confusing. $10,068. Okay? All right. So what I want you to do, I want you to interpret the interval. Go ahead and interpret the interval. What 95% confidence means. I want you writing that down. I'm still seeing some folks struggling with this concept. We want to make sure that we can do this. And yes, use the posters.
Okay, have somebody else read your statement, see if you're on the same page. You guys think you've got those two? All right, let's take a look. Should have had something along these lines. So to interpret the interval based on our sample, we're 95% confident the true average loss in home value is between, make sure you've got dollar signs, $9,052 and $10,068. How are we doing with that? I want it to be formulaic for you. I don't want you to have to stop and think too much about it. I want to just kind of roll out there. And to explain what 95% confidence means, that's interpreting the level. If we were to take repeated samples, 95% of the resulting 95% confidence intervals should contain the true average loss in home value. Okay? You all right with that? Questions? So I'm calling this the baby version because I just gave you these bits and pieces. We didn't need to do that step. That step is probably the most challenging thing that you're going to see. And it's not that it's hard, it's just that it's tedious. Okay? So along these lines, still with this problem, we're just going to kind of think about the answers that we got, read these problems, and discuss with each other. What do you think? Okay. So what would have happened if my standard deviation had changed? Instead of 1,500, it's now 3,000. Simon Hermana? It's double. Yeah, the standard deviation is double. What would happen to the width of the confidence interval? What do you think? Bigger, smaller? Bigger? It's not. Standard deviation is not taller. It's the width. Width of the confidence interval. Hang on one second. Hang on one second. So if we go back to what we had here, ladies and gentlemen, we're talking about the width of the confidence interval. This here is my margin of error. I'm not changing the t-star. Well, I kind of am because of degrees of freedom. No, actually same sample size. I'm changing the standard error. Is my standard error going to be larger or smaller? It's going to be larger. And if my standard error is larger, what's going to happen to the whole confidence interval? Larger.
Okay? All right, back to the questions. Your classmate suggests changing your confidence level to 90 instead of 95. What's going to happen? The margin of error will get smaller. Everybody okay with that? Because it's like me predicting. Yesterday I was telling some folks I predict tomorrow's high temperature will be 52 degrees. Or maybe that was your class. I don't know. I said I'm going to say plus or minus 2 degrees. Yeah, I wasn't very confident in that. It's going to be colder than that today. So if I want to be more confident, I need more things to fall in. So also if I'm going to be less confident, it's going to become narrower. Now, Steve's asking me, instead of changing the confidence level, would it be more statistically appropriate to draw a bigger sample? Is drawing a bigger sample going to be something that helps me bring in my confidence interval? Yes, right? Why? Beautiful. Abso-freaking-lutely. The place where the sample size comes into my formula is with the standard error, because the standard error is S divided by the square root of n. If I make n a bigger number, it's going to shrink your standard error, therefore shrinking your confidence interval width. Your margin of error cuts back. Now there's a problem with that. We still have to kind of abide by that 10% rule. We can't have more than 10%. But also, one of the things that we come across in the real world, it's either too hard to do, or it's too expensive to do, or it takes too much time to do. So bigger is better, yes, if you can do it. It does. It does change T star, and actually as you change your T star, larger sample sizes, the T star is going to go down because it starts to get closer and closer to the normal model getting smaller. So yeah, it's a good thing on a couple of accounts. But again, it's this idea here where it says it may not be practical. Okay, it's just like when I ask you, somebody rejected the null. They found evidence that a change occurred. Why would they not do it? Well, you might have that the cost of the program outweighs the benefits. Real life gets in the way sometimes. Real life stinks. All right. So I want you guys to go through problem number 18 on your own. Do it, do it, do it. Here we go. We're going to go through this. Now, I didn't write down the given stuff here simply because I wanted it all to fit. But you can see what my conditions are. First off, this was not a random sample. Did you notice that? And when it's not a random sample, we have to state that we hope it's representative. Because that's the next best thing, but we don't know for certain. And if someone were to come back and criticize this study, that's probably the first place that they would go to. Now, 44 is definitely less than 10% of all work days, and hopefully it should be large enough to assume that the sampling distribution is normal. I mean, we are talking about a parking lot here. You can only fit so many cars in a parking lot. So you're not going to say I only have like 120 cars in the parking lot, but all of a sudden one day I hit 1,000. You only have so much space. Come on, give me a break. So we're doing a 1 sample t interval. Did you state that? 1 sample t int. We have degrees of freedom is 43. Did you get that part? We're good? And so we're going to be centered at that 126. I don't have the sampling distribution up here. So we're following a sampling t distribution with 43 degrees of freedom, centered at 126, the standard deviation of 15 over the square root of 44. My t star, and being 1.68, do 1.681, that's okay, I don't care. It's not the deal breaker. So far, so good. Okay. Resulting confidence interval. Now, we're not talking about the thousands of dollars here, so it might be nice to include some decimals. So I would say interpreting my level or my interval based on our sample, we're 90% confident the true mean or average daily income of the parking garage is between $122.20 and $128.80. We're including the fact that it's the true average. I don't care if you use the word mean or you use the word average. It's okay. The confidence level, 90% of repeated samples. If you put the size in there, that's great. It's not a deal breaker for that. Will produce confidence intervals that contain the true average daily income of the parking garage. Remember, your level is generic. You should never reference your specific interval when you are interpreting a level. And then my entire interval here was below that 130. Don't think, well, it's close. I don't care how close it is. It's not in it. Okay, we built in wiggle room. It's not even within the wiggle room. Because it is all less than 130, my evidence indicates that the average is actually lower than $130. I would not agree with her claim. Is it feeling similar enough to what we had been doing? That's really my goal. Now, we do have one slight change that comes with this unit. No, we've already talked about it. And that is when we're talking about means, it's just a yes or no where we're counting yeses out of total. We actually have values. So we are going to have situations like this, where you have a histogram. Hey, Merry Christmas to you. You don't have to type in all 201 values into your calculator. Cha-ching. Thank the Lord, right? Because that would really stink. So go ahead and read this problem. We'll just walk through this verbally here. We don't need to write it all down. But I do want you to do the calculations for B. Okay, somebody give me an assumption. Sam. Independence. Wow, she was right there. She's amazing. Independence. Do we have independence? Well, I kind of question that. Have any of you guys ever traveled via air? Flown? And I personally, I overthink everything, just letting you know. So I'm on the same boat that a lot of you guys are. I overthink everything. I'm going to say, no, flights really aren't independent because it depends upon what? The weather, how busy it is, the plane itself. Plane itself is hopefully going to be independent. If one train, the train. If one plane breaks, it's probably not going to break another plane. But they do have to deal with the same conditions. So I can't really state 100% independence. So what do I check next? Kayla. Random. Do we have random? I don't really see that. So if we don't have random, what do we say? Say it again. Hopefully representative. There you go. We hope it's representative. Okay? Then there's what? 10%. So I have here 201. 201 has to be less than 10% of all flights from 1995 through September 2011. Okay? What else? One more condition. Nearly normal? What do you think? What's my sample size? Very big. That's a technical term. Very big. So what happens when my sample size is really big? We have a little bit more. I mean, yeah. And that is generally unimodal. skew that. There might be some stuff going on. But 201, that's a freaking big sample. I don't see any massive red flags here. I don't know. I have a feeling these were probably some like blizzard days. But nothing really jumps out at me. So by what can I say nearly normal? What allows me to kind of say a large enough sample? Boom! I don't know why I did that. Central limit theorem. Central limit theorem, that's a really good size sample. We can assume that the sampling distribution itself is going to be normal. All right, did you calculate your 90% confidence interval? What was your low end? One more time, Eden. Why are you looking at me like that? I was like, you had just said it, so I was going to repeat it. 80.27? 16? Okay, really close. What's the high end? 81.28? 8, so 81.29, whatever you want to do, that's fine. And then the interpreting the confidence interval. Who wants to tell me what the interval is? Interpret it using words. Yes. Blah, 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 blah. Yes. And this is a little bit weird because, yes, our display here is about percentages. But that percentage itself is a number from each day. So basically, we're looking at each day, yes or no, you left on time. We're getting a percentage for that. Then we're turning each of those days into a on the histogram. So to interpret this, we would say we're 90% confident that the true mean monthly or whatever percentage of on-time flight departures is between 80.22 and 81.29. The sample size is pretty big there. That allows me to kind of keep that range smaller. Okay. I want you to write down your answer to this. You don't need to do much work. But I want you to write down your answer using words. It's one thing to kind of understand what it means. It's another thing to be able to explain it. And this was something that we struggled with a little bit on the last quiz. Okay, so one of them focuses on the population, one of them focuses on our sample. But what about tying the two together? Tying together hypothesis tests and confidence intervals. It's not if they have the same alpha, because you don't have an alpha interval. So in this case, I have a 90% confidence interval. You okay with that? Now, my alternative hypothesis. Would my alternative hypothesis been a one-sided test or a two-sided test? Why is it one-sided? Because we're looking for less than. So if I had to go from my confidence interval to a hypothesis test, 90% confidence interval, one-sided hypothesis test, what would the alpha have been? 0.05. You guys okay with that? Because whenever we're making our decision, I gave you a p-value. You always have to tie your decision, your p-value, and your alpha all together. And see, that's what we have here. Confidence level, p-value, and decision. The decision is made based on alpha. So would you come to the same conclusion if the p-value here was 1.142? Was the 325 in my interval? So 325 is in my interval. would we say that it, do we have evidence that it's not meeting? Do we have evidence that the mean sodium content is less than 325? Less than 325 is my null. There's my interval. Would you reject or fail to reject? $325 lies in the interval, correct? Would you reject or fail to reject? Fail to reject. The null is that there is no change. The alternative is that it's less than. Okay? So since the 325 falls in our interval, we can't say that it is lower than that 325. Okay? Because I have some values that are higher. So based on the confidence interval alone, I would have failed to reject. The p-value of 0.142 is greater than the corresponding alpha of 0.05. So with that, we would also fail to reject. See, this is what we got here. 90% confidence interval contains the 325. That means I cannot say it's less than. Part of my interval is bigger. They used an upper tail test, or one-tailed test. So the p-value should be more than 0.05, and it was. So you're coming to the same conclusion with that. But what I'm trying to get you guys to see here is hypothesis tests and confidence intervals should always back each other up as long as your alpha and your confidence level support each other. Okay? One-tailed test, divide by 2. Two-tailed test, don't. All right, so the mechanics for a one-sample t-test. When we were talking about proportions, we found our test statistic. What was our test statistic for proportions? Z-score. We found that by doing what? Using words, what did you do? Observed minus expected over the standard error or standard deviation. Hypothesis tests are focused on the hypothesis, so that's why we look at the standard deviation. So for this, if you have your assumptions and conditions met, just like in the proportion tests, to test the hypothesis, your test statistic, again, you must talk about the degrees of freedom here. This is the same thing. Observed, that's y bar, minus expected, mu sub 0, that's just what you have in your null hypothesis. Sub 0 is always talking about your hypothesis. Divided by the standard error, where again, standard error is still s over the square root of n. And we still have to talk about the t-distribution always needs a degrees of freedom, because depending upon what your degrees of freedom are, everything, all your probability, everything changes. I know. It is a lot nicer for this. T-score. Mm-hmm. Instead of a Z-score, it's a T-score. I know. The nice, like I said, that unit 5 is the last time we see like truly new material. Past that, we're just kind of tweaking what we know and pulling it all together. So we're talking about means right now. When we're done with means, we're going to talk about counts, which is actually just one chapter in the book. And when we're done with counts, we've got to go back because we skipped unit 2. And we did that specifically because it fits right in with chapter 27, which is our linear regression tests. And that should go pretty fast and easy. Okay? That's it. Mm-hmm. 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 Yeah. Not really. because our exams are in May. Last one. But I'm pretty much anticipating those 2 weeks I don't really see you. So we have as much time to review. We'll have time to take a practice AP exam, so that's 2 days in class. And then we kind of like review. But it's not like... Yes. Yeah. All right, so we have this. Because now I'm going to switch things up a little bit. The one thing that's different with means versus proportions we're just kind of counting yeses and nos. Means, we actually get a whole bunch of different values. So if you take out your note packet. Now this here says Practice Quiz Chapter 22A. We've been doing these all along. I had just stopped calling them practice quizzes and really didn't feel like retyping up the notes this time. So I left the practice quiz thing in there. So all of those reviews that we did in class that felt like the quiz pretty much were the quiz. It's just like this. Okay? So you should be seeing a page, and typically your free response question looks like this. Now, what's a little bit different here, okay, what's different here from what we've done in the past is I'm not giving you 15 said yes, 12 said no. I'm not giving you something like that. I'm giving you all the data. If I give you data, what do you think you should do with it? Plug it in. Plug it in where? Stat, edit, list 1. Put that puppy on in there. I'm done entering my data. Are you done entering yours? How did you do yours? Okay, so you took the longer way. I purposely tried to do something different than what you would have done. Okay, so I purposefully said I'm going to do it the way that I don't think you're going to do it. Because I like to mess things up sometimes. I think it's more fun that way. So what I did, take a look. What did I do? Yeah. What I did is I created a list of the different values. And because it was in order, I just put the number of times I saw each of those values. So I purposely switched this up so that you could see how to do both ways. You know that you can put every single number in your list 1. You can also create what's called a frequency list. All right? Okay. Now I'm going to quit out of that. We are testing the appropriate hypothesis. We're going to write all this down, but I'm going to focus right now on the calculator. We're going to test the appropriate hypothesis. What am I going to do? Stat, test, just the t-test. Okay, so if you look at t-test, you have the option of putting in your statistics or putting in your data. I've made a list of data, so I'm going to use that option. We'll come back and talk about the mean and everything else. You would just have list 1 and 1. The method I would choose, because I had a frequency list, okay? We're going to come back to that. Let's start working through what we would need to show. Okay, so we've got our questions. I am not going to ask you to write down every single data point. You need to do that. It's up to you. But when we go through this, we're doing a hypothesis test. So for my hypothesis test, I need to start with what the hypotheses are. So I'm going to have the null hypothesis and an alternative hypothesis. What is my parameter of interest here? What am I trying to learn about? Okay. Are we doing proportions? We're doing averages. What is the parameter notation for averages? Mu. So we'll have mu equals, and then mu with something else. Just like with proportions, if you leave the p off, you totally lost those points. For means, you have to use mu. Now, what are we claiming the average is? We're claiming the average is 15. So mu equals 15. And I know for the alternative, I'm still going to have that number of 15. Now, it says we have our random sample. We're looking to see if this indicates they're taking more credit hours. So what would my alternative hypothesis be? Greater than. So let's go back to the calculator. So what do I put for mu sub naught? 15. That's mu sub 0. That's no change. My alternative is greater than. Now what we've done is we've put all the stuff into the list. So this is really nice because when I hit calculate, it gives me a whole bunch of stuff. The order that I want to see you guys list these out is like this. These three first here. So I'm going to say X bar, you can say Y bar, I don't care. But in this case, it is 16.625. Is that what you guys got? Okay. I'm going to say S is, I'm just going to do 2.22. And N is 24. So that's like doing your 1var stats, you get it all. You have to identify it. What have I not done? Assumptions and conditions. So to check my assumptions and conditions, what's my first piece? Independence. So do we have independence here? We're told a random sample. What else do we need? Careful. What's my sample size? 24 is less than 10% of what? 250. I wouldn't do that to you. You just know that you're kind of on the edge. So 24 is less than 10% of 250. And then what's going to be my next assumption and condition? Normal model. How do I check the normal model? Draw it. So I'm just going to kind of quit out of this. I can come back to it. I have all of my data in my table. How do we graph this stuff? Do you remember what to do? Because it's been a while. Second, stat plot, because yours has probably been turned off. Turn it back on. Now I want you to look here. Did you do second y equals? Turn the first one on. And then look at this. This is important, guys, because you have to be able to tell which ones you can and cannot use. Not this one. That's a scatter plot. This is connecting the dots on a scatter plot. This is a histogram. Box and whisker with outliers, just box and whisker. This last one here, that's the NPP. Let's start with the histogram. Now you have all of your data in list 1. I did put a frequency list in mine, so I'm going to add that there. I'm going to quit out of it. And I'm just going to hit what? Zoom stat. Zoom stat. And I am literally going to sketch this. And I'm going to label this credit hours. You don't even need to do that. Do you guys see did you get a graph similar to mine? Do you notice how I'm not caring about bin widths or anything like that? Just trying to sketch the general idea. You could also, in your plots, I actually really like the NPP plot. But if you're doing an NPP plot, you have to have it all in one list. So we'll come back and I'll do that next time. The histogram is just simple. Make sure you title your histogram. My histogram is about credit hours. So, my sample size is 24. What would we say about that histogram? Do you see outliers? Do you see heavy skew? So I'm just going to say normal enough. Now, we could get crazy here. And if I wanted to really do this, I could say my smallest credit hours was 12. My largest was 21. I'm going to count by ones. Go to, I think my highest number was 6. Whoops. And that is what the actual data is. If you wanted to get specific, you can. How about that data? What does that look? That looks pretty good, right? So what you want to say, guys, if you're just doing zoom stat, there's nothing wrong with it. You just don't want it to be ridiculous. You don't want to see some, like, whoom, going down like that. You don't want to see, obviously, kind of like a mode over here and a mode over here. So this is normal enough. So what we get to do here is we're going to assume the sampling distribution follows what model? T model. How many degrees of freedom? That is centered where? Centered at 15. This is a hypothesis test, so we're going to be centered at the hypothesis. Problem is with the standard deviation, do we know the standard deviation of the population? So we're going to have to use what our sample said. So what am I going to do for my standard deviation? 2.22 divided by the square root of 24. Okay? And we are going to be doing what? Well, one sample t-test. For one sample t-test, What is my test statistic? T star. Well, not T star, just the T score. And you might have probably said that. With how many degrees of freedom? And that's found by doing what? Yep, you're observed. Minus expected, which was divided by what we had for the standard deviation. Bless you. And if we go back to my test again, it still gave me the information that I needed. So I'm going to say my T-score is what? What is it? 3.58. What do I need to write next? The probability statement. Good. Had a couple of folks forgetting this. The probability that we have a T of 23 that is alternate symbol greater than 3.58 is what? Quiz. Oh, yeah. Yeah. So what am I going to say here? Do you see that right there? If you told me 7.89 or 7.9, no, you would have gotten no credit. A p-value is a probability. Probabilities have to be between 0 and 1. Do you see that out here? They give you that out there? Just basically put 0. I mean, if you wanted to write it out, you would say 0.123, and then it would be 8. No, don't write it in scientific notation. So what would you do here? What would you do? What would your conclusion be? With a p-value approximately 0, which is less than 0.05. We can go with the standard. What do? We reject the null. We do or we don't? We do. We have. I don't know how to spell enough all of a sudden. That was special. We have enough evidence to claim, and this is why we should have written out at the very beginning, what does the mean here talk about? Average credit hours. So we need to make sure we do that. Claim the average credit hours is what? Is one more time? Greater than 15. Okay, not quite yet, guys. I still have you. The last thing here it said to do was find a 95% confidence interval. Guess what? We don't have that much to do. because we've done all of the work for the for the confidence interval, I can say assumptions conditions met. Met above. But my sampling distribution does change here. It's still T star with 23 degrees of freedom, but what changes? Does the center change? Yes. What does the center change to? 16.625. My standard deviation, does it change? No, because it's still the same thing. So 2.22 over root 24. And I'm going to do a 1 sample z int, or sorry, not z int, t int. And basically all I need to do is I can say y bar or x bar plus or minus z star of 23 times sc of y bar, t star. I keep doing that. Look, I just erased the top part. Perfect. And t star of 23 I need to find. How do I find that? Inverse t. We are doing 90 though here with 23 degrees of freedom. So I get 1.71. And then I can just go to stat test. I know I'm going through this kind of fast. And I'm just going to do t interval. But look, again, the data is all in there. My confidence level is 90. There you go. Huh? Oh, it does say 95? All right. So you guys are going to have a quiz over this stuff next class. I'll have an example problem posted. Maybe we won't do the quiz next class. We won't do the quiz next class. And I'll extend the homework also. But please look in your notes for the marshmallow investigative task.